So with that, we have started the recording. So today's lecture will be mainly regarding so-called effective potentials, which is essentially that we are going to take a system that has a number of degrees of freedom and reduce it to a smaller number of degrees of freedom. And we will cover essentially two different types of cases where this occurs. Write that down. So, as I said, what we will be discussing is so-called effective potentials. And the first type of situation where this occurs is when you have different types of constraints on your system. So let me first go through the general theory, and then we will go through an example. So we're going to consider a system where we have n generalized coordinates. I'm going to call those capital QA. So this refers to our larger number of degrees of freedom that we want to reduce. And we will assume now that this system has a number of holonomic constraints. Rather, I will assume one holonomic constraint. So that is a constraint on the form that we have some function of these coordinates and possibly time, which is equals to 0 or some constant. It doesn't really matter. You can choose f such that this function is 0. Now, based on this constraint, our system is going to have fewer degrees of freedom. For example, if I have motion in 3 dimensions, but I constrain that motion to a surface, I'm really moving in 2 dimensions. So based on this constraint, I can write QA as a function of some coordinates regular Q and time, where QA A goes from 1 to n minus 1. So we have n minus 1 coordinates and time. So these functions depend on that. And by the chain rule now, so if I want to know the time derivative of the capital Q's, we have the following. If I take the time derivative of that, I'm going to get is the partial derivative with respect to time of QA plus Q dot A dA QA, right? This is just a chain rule for these functions QA. And now this system is going to originally be described by some Lagrangian. So we're going to assume that our Lagrangian is given by 1/2 MAB Q dot A Q dot B. And then we're going to assume that we have some potential V of Q and T. Now, if we have this constraint, then we can rewrite this by using this relation that we have from the chain rule. So if I just insert this into this Lagrangian, what we will end up with is the following. So 1/2 MAB will still be there. And then we are going to have dt QA, dt QB plus 2, and M here is assumed to be symmetric, so I can write, this is why I get this 2. And we will have dt QA times Q dot B dB QB plus the final term Q dot A, Q dot B, and then we have these dA QA, dB QB, minus this potential, which is a function now of the small q's and t's, because the capital Q's are functions of Q and T themselves. So if we now assume that a further assumption is that if we have these time derivatives of QA, MAB, and then and then we take dBQB. If this is equal to 0, then this middle term is going to give us a 0 as well. And in that case, our Lagrangian, our effective Lagrangian, is going to be of the following form. So we're going to have 1/2 MAB Q dot A Q dot B. There we are. So again, our effective potential is now in this form. So we have a kinetic term and we have a potential term. And this, just to say, this MAB here is the effective inertia, and it's given by our original MAB with capital indices times dA QA dB QB. So this is just comes from, sorry, not that term, but this term over here. And our effective potential, it gets contribution both from the original potential here, but it also has a contribution from this part here, which does not depend on the derivatives of the small q's, but it only depends on the small q's themselves and possibly time. So this effective potential is the original potential minus 1/2 MAB dt QA dt QB. So this is the effective inertia. This M with the small indices, and this potential here is the effective potential.
Could you please scroll a bit, because the recording icon is in the way of what you're writing. So.
Yeah. Okay. Sorry. There.
Oh, thanks.
Any questions so far?
Yeah, I have a question.
Yeah.
Can you hear me? Your assumption, this assume DTQA MAB.
This assumption.
Yeah. Why? Where does it come from?
Yeah. So this is not necessarily going to be true. This is just an assumption now to get the effective Lagrangian on this exact form.
Oh.
What it is essentially telling us is that with the kinetic metric that we have, so with this metric MAB, that the change in the capital Q's when you change t is orthogonal to the change in the capital Q's when you change the coordinates.
Right.
We don't have to do this assumption. If we don't make this assumption, then we're going to have some extra terms here, which is essentially going to be based on those terms. But those terms are only going to have a single time derivative. We're going to see a little bit of examples with that a bit later today. but just in order to keep it on this more simple form with just the kinetic term and just a potential term, I made this assumption.
All right, thank you.
Okay, so
I have a question.
Yeah, sure.
If it's okay.
Of course.
What does it mean to like have an effective potential and an effective Lagrangian? Like, what is it we're actually doing here?
So as I mentioned in the beginning, what we're trying to do is that we take a system that has a larger number of degrees of freedom, and then we are adding a constraint on top of that, and we're seeing what the potential becomes in that new system, essentially.
Okay.
So in the system where I have 1 degree of freedom less, or even more degrees of freedom less, I can have several constraints.
Okay, and that depends on lower capital A, right?
Can you say that again? Sorry.
Does that depend on lower capital A, the letter A, which goes from 1 to n minus?
Yeah. So the capital indices here go from 1 to n. So that means that they are the original coordinates.
Mm-hmm.
And the smaller letters go from 1 to n minus 1, or even if you have more constraints, n minus whatever.
Okay.
I think it would be a bit more transparent if we take an example.
Absolutely.
So let's do that. So the example we're going to go through is a bead on a rotating ring. So if I take a ring like that, well, it was supposed to be horizontal, but let's imagine it is. And we have some axis of rotation here. We can have a bead that is allowed to move on this ring, but the ring also rotates with some angular frequency omega. Now, a priori, if this bead has mass m, I could describe the bead's position using Cartesian coordinates, for example. That's 3 coordinates. So the 3-dimensional description is that we have x, y, and z, our 3 coordinates. Or if you will, we could use also spherical coordinates. So r, theta, and phi. However, if this bead is restricted to move on the ring, it really only has 1 degree of freedom. And that's essentially the angle theta, right? So the constraints here are first that r is equal to capital R, where capital R is the radius of this ring. And we also have a constraint that the angle phi in spherical coordinates, that's given by some angular frequency times the time. So these are 2 constraints that we have. These are corresponding to these functions f of q and t. In the case of r, there was no dependence on neither the coordinates nor time. That's perfectly fine also. And here we have a dependence on time. Now the Lagrangian in the 3-dimensional coordinates, that would be m½ times the velocity squared, and then we would also have the potential, which is mgz if we have a gravitational field g. So now if I implement these constraints, and I also use the angle theta as my remaining parameter, then I can rewrite all of this as m½ let me first write the Lagrangian in spherical coordinates. So in spherical coordinates, we have r dot squared plus r squared theta dot squared plus sine squared theta phi dot squared minus mgr cosine theta. So what happens now when I insert these constraints is that, well, r dot here is 0 because my constraint is that r is a constant. Phi dot is going to be omega, because if I just differentiate phi with respect to t, I get omega. And so I can just insert this here. And I'm going to end up with m r squared over 2 theta dot squared plus sine squared theta omega squared minus mg r cosine theta. And now this Lagrangian only depends on the theta and theta dot, right? So just to separate here the kinetic and potential parts, I'm going to write it like this. So I have mr squared half theta dot squared minus mg r cosine theta minus m r squared omega squared over 2 times sine squared theta. So this is the kinetic term, or the effective kinetic term. And this part here is the effective potential. Right. So from having this 3-parameter description, having our Lagrangian with 3 parameters, x, y, and z, or r, theta, phi, we have a Lagrangian with only 1 parameter, which has a kinetic part and a potential part. So if we just look at how this potential behaves, so let's draw this as follows. So of course theta now goes from 0 to 2 pi. We have 0 to 2 pi as our range for theta, and in the middle we have pi. So we're going to have 2 contributions to the effective potential. It's first this, which is the original contribution, and I'm going to draw that in green because I did so here. So this is going to look something like, if I could draw, it's going to look something like this, right? So this is mgr cosine theta, and then we're going to have a contribution from the rotation. That's going to look something like this. So it goes down like this and up again. And so the effective potential is the combination of those two, which means that it's going to look something like this. No, I should draw it properly like this, right? So this is the effective potential. And you can also see what happens when we increase or decrease the speed of rotation here, and kind of how the system is going to behave depending on that. So for example, if we put the rotational velocity to 0, then we're going to get rid of this rotational part, and essentially what's going to be left is the gravitational part. We're just going to have a standard pendulum. And in that case, we have a minimum, and it's at theta equals to pi. This is essentially just your regular pendulum swinging back and forth. However, if you start increasing and increasing the speed at which this rotates, eventually, so you can see that at pi, the second derivative of this original potential term and the addition due to rotation, they have different second derivatives. So once the rotational term starts taking over, the effective potential is going to develop two minima that are displaced from theta equals to pi. So what happens then is essentially your minima of the potential starts moving away from theta equal to pi, and they instead move up on the ring. And eventually, if you spin very, very fast, so that, or if you have very low gravity, then this term takes over completely, and you end up with these two minima of the potential. So if you spin really, really fast, then your two potential minima are going to be located at pi half and 3 pi half, which is also kind of intuitive, because that's essentially what you would expect from the centrifugal force in the spinning in this rotating frame. Are there questions on that?
So even with just a little, like a small value for omega, the potential minima is displaced. It's not.
Not necessarily. No, it's not displaced even for a small. There's a critical value.
Because
So
I'm looking at the red graph and I'm thinking it already has two minima, right?
yeah, but I mean, this red graph can look in different ways. I mean, it does not necessarily have two minima. So the main thing is, what is the second derivative at pi, right?
Okay.
So if the second derivative is positive, you're just going to have one minimum. If it's negative, because the rotational term is taking over there, then you're going to develop two minima.
Okay.
So you can compute a critical angular velocity where this happens. If you take the second derivative of this term, well, if you take the second derivative of both terms together and check, is this positive or negative? If it's positive, you have the global minimum here. If it's negative, then you have something like this, because you have a negative derivative there, which means that you're going to develop your minima here instead.
Okay.
Does that make sense?
Kind of. I think I'm gonna have to ponder about it.
Yeah, I mean, the easiest way to see this is just to compute the second derivative here and check when is this second derivative positive and when is it negative. So, I mean, it's not enough just to have, I mean, it also kind of makes sense, right? If you turn it very, very slowly, it's not going to make your bead go off really from the base, but there is a critical value where it becomes unstable, the lower minimum. Okay, so that's the first kind of effective potential. The second kind that I wanted to discuss is when you have effective potentials but they are due to constants of motion. So what we just did was rather straightforward. Essentially, we only needed to replace this constraint into our system, and then essentially we got the effective Lagrangian out immediately. This next thing is not as straightforward. So what I'm going to do is the following. I'm going to assume that we have some Lagrangian, and that it's given by 1/2 MAB Q dot A Q dot B minus V of Q. This is a pretty standard assumption, right? Furthermore, I'm going to assume that there is some symmetry of the system, and we discussed this last time with regards to the Noether theorem. So that I'm going to assume that the Lagrangian does not depend on one of the coordinates for some C. So that some fixed C. So for one of the coordinates, the Lagrangian does not depend on that coordinate. It's still going to depend on the derivative of that coordinate through this term, but it's not dependent on the coordinate itself, right? So according to Noether's theorem, this means that we are going to have a constant of motion which I'm going to call J, which is equal to the L dq dot C, right? And that I'm going to write in the following way. So let me call let me make the following denotation. So I'm going to call QC, I'm going to call capital Q. So this is the degree of freedom that I'm going to get rid of. So I mean, for example, we can assume that C is equal to M, so that is the last coordinate we're going to get rid of. And if this is the case, then this is equal to the L the capital Q dot. And if we just look at this Lagrangian, the capital Q dot, I'm going to get that term from this term when one of the indices is equal to C. So I'm going to write this as mu times Q dot plus lambda I Q dot I. And now I goes from 1 to n minus 1. So I takes all the value except for C. And this mu here is equal to m n n. And lambda I is equal to m n I, which is of course also equal to m I n, because we're assuming that m is symmetric. So this is just taking the derivative of this term essentially. Okay, do we have any other constants of motion here?
In time, maybe?
Yeah, so note here that I did not write out any explicit dependence on time. So the time translations is also symmetry, and we know that then the Hamiltonian is conserved. So our second constant of motion is the Hamiltonian, which then takes the following form, 1/2, and now I'm going to separate the sums over the i's and j's and the contribution from the coordinate that we're trying to get rid of. So I'm going to have mij q dot I q dot j. Those are just the contributions from all the coordinates that are less than n, that are not equal to c, plus 2 lambda I q dot I times q dot plus mu q dot squared. And then we have the potential. And note that the potential by assumption is not a function of the capital Q. It only depends on the Q's, which we're not trying to get rid of, because the derivative here with respect to Q was equal to 0. Okay, so what we now know, or rather what I'm going to try to do, is that I'm going to try to get rid of all of the dependence on capital Q from this expression for the Hamiltonian. And you see that we can do that because neither mu nor lambda are going to depend on capital Q, because if they did, then our Lagrangian would depend on Q. We also have this constant of motion J, which includes Q dot. So I can solve for Q dot from this expression, and I can insert it into the Hamiltonian.
I have a question about
Yes.
the Hamiltonian real quick. Why do we take minus the potential?
Ah, sorry, that's a mistake on my part. It's already in the lecture notes. It should be plus the potential. Very good. Okay, so what we're going to do here is to make this replacement. We're going to take Q dot, and if we solve for Q dot, it's 1 over mu J minus lambda I Qi dot. Right? This is just solving from the expression from the constant of motion. And this will put your Hamiltonian on the following form. So we're going to have 1/2 Mij minus lambda I lambda J Q dot I Q dot J plus 1 over mu, times the A squared. And then plus this potential V of Q. And so this is what we're going to define as our effective Hamiltonian. And we're going to split it in the kinetic part and into the potential part, just as we did before. So the kinetic part is going to be this guy, which depends on, which is second order in the derivatives of Q. And then we're going to have this part, which depends only on the coordinates Q themselves. So this is equal to 1/2 Mij Q dot I Q dot J plus the effective potential, depends on Q. And here Mij is then Mij minus lambda I lambda J, while the effective potential, well, that's the original potential V of Q plus J squared over 2 mu. And so what we have done now is to eliminate the variable Q from these equations. Just replacing it essentially by this constant of motion that we had. Any questions so far on that? Okay, I think this will also become a bit clearer when we go through some examples. So the question is now, can I use this directly as my Lagrangian, or rather, can I use this kinetic part and this potential part and reinsert, kind of use my Lagrangian as the kinetic part minus the effective potential part? And the answer is no. So just to say that our first guess, that would be that our effective Lagrangian would be equal to 1/2 Mij Q dot I Q dot J minus the effective potential. So I'm going to call it Lagrangian effective 0. So that would be our first guess. So the point here is that we know that J is a constant of motion, and we know that H is a constant of motion, and that this H being a constant of motion, well, that would be the case if this was the Lagrangian. But we also need to reproduce all of the other equations of motion that we have in our system. So the Hamiltonian being constant just replaces one of the equations of motion. We also need the other equations of motion to coincide with the equations of motion that we would get from the original system. So in order to do that, we're going to note that any effective Lagrangian of the following form, so if I take 1/2 Mij q dot I q dot j minus the effective, but I also add a term which is on the form q dot I and then some function kappa I that only depends on the coordinates q, then this is also going to lead to the exact same Hamiltonian being conserved. And that's because this term that I added here, it does not do anything to change the Hamiltonian. It gives a contribution both to the term which is a derivative with respect to q dot, but it also gives a term which has the derivative with respect to q. And those two terms in the definition of the Hamiltonian are going to cancel out. And so it's going to give you the same Hamiltonian. So just from knowing that the Hamiltonian is conserved, we cannot directly reconstruct the Lagrangian without knowing the other equations of motion from our original Lagrangian. And it's now 2, so we're going to have to do that after the break. Are there any questions?
Yeah, sorry, what was kappa again? I missed that part.
Kappa is now any function of q.
Okay.
So the point here is that if I make this addition here to the Lagrangian, it's going to reproduce the same Hamiltonian.
Mm-hmm.
So what we're going to do after the break is to determine kappa in such a way that I recover the rest of the equations of motion.
Okay.
So that will be our goal to start with for the next hour. Other questions? If not, let's have a break there and we reconvene at 1/4. And so just to recoup a little bit what we said in at the end of last hour, we had this Hamiltonian, or this effective Hamiltonian, which we now know is conserved. We know that J is a constant of motion. And the question is, what effective Lagrangian gives us the same remaining equations of motion that our original Lagrangian gave us? And we also know that if we take this effective Lagrangian, or this family of effective Lagrangians with this kappa being arbitrary functions of q, then this is going to lead to the same Hamiltonian being conserved. So our goal now is to find out what choice that we should make for these kappas in such a way that we reproduce the original equations of motion. So in order to do that, we are going to take the original equations of motion, which are the following forms. So we have the L, the Qi, minus the dt, the L, the Q dot I, and this should be equal to 0 because that's the remainder of our original equations of motion. And I'm not going to go through all the derivation because it's rather tedious. It's like 6 lines in the lecture notes. If you want to know exactly how this goes about, the computation, it is available in the lecture notes. What is important and is the end result. And so the end result is going to end up being the following. So DL F0, so our original guess for the equations of motion, dt dl F0 dq dot I. But we're also going to get a contribution from additional to this. And that contribution is going to take the following form. We're going to have j q dot I di acting on lambda. Let's get the, sorry, this is a qj. This index is a j. Lambda j divided by mu minus j and then d dt acting on the same thing. So lambda I divided by mu. And this should be equal to 0. So this is our original equations of motion, just that we have inserted the fact that we know that j is a constant of motion now. And the expression for j in terms of q dot and everything. Now, if we take this effective Lagrangian and we derive the equations of motion for that, we're going to get the same thing. So dl effective dqy minus d dt dl effective dq dot I. So separate now this dl effective 0, which was our original guess without this kappa term, and this effective Lagrangian where we have added the kappa. So we get again the same thing here, this 0 terms but in addition we get two terms based on kappa. So we're going to get let's see, we're going to get plus d q dot I kappa I dqi minus d dt dq dot I kappa I dq dot. Sorry, there are too many i's. I should use j's instead. So let's use j's as the summation indices here. And then a j there. And this should be equal to 0. Now, what we want is that both of these equations of motion are the same, because we want to use the equations of motion in our effective theory. And we see that this is possible. So the equation of the original or of the original system are reproduced if we choose kappa such that kappa j is equal to the constant of motion j times lambda j divided by mu. So in order for us to reproduce the original equations of motion, then this is the choice that we need to do. And so that tells us what our effective Lagrangian is in this case. Questions on that?
Your voice kind of lagged when you explained why we chose kappa to be that. So
Yeah, sorry, I can retake that. So the point was that we want this equation of motion, which was our original remaining equations of motions after we have taken care of the constants of motion, so the Hamiltonian and J. We want those to be exactly the same as those that we get from our effective Lagrangian.
Mhm.
And since those terms are the same, those terms need to be the same. And if we just identify here, we get out that this is the case if we choose our kappas in this way. A priori plus a constant, but that constant doesn't really matter for the equations of motion at all. Is that good?
Yes.
Yeah. So just like before, I think this will be a little bit clearer if we look at an example. So the example that I'm going to take is the following. So let's take a sphere, and let's study motion on the so motion on the surface of a sphere. So this can be essentially any mass restricted to move on a sphere. So the typical example would be a spherical pendulum, which is essentially just a mass hanging from a pendulum, and it can move based on being fixed in a single point. That pendulum would move essentially on the surface of the sphere, right? So in that case, we also have, let's do the following. So we have our mass moving on the surface of this sphere, can move essentially as it wants, and we also put the gravitational field in just for show. Or yeah, let's do that. So the Lagrangian in this case is going to be given by 1/2 m r squared theta dot squared plus sine squared theta phi dot squared minus mg r cosine theta. I mean, you can arrive at this Lagrangian by considering first the motion in 3 dimensions and doing the effective potential as we did during the first hour. But this is now a 2-dimensional Lagrangian with motion on the sphere. So the capital Q that we were talking about here, the symmetry of our system is going to be rotations around the z-axis. And this is not going to change the system because it's essentially rotations around an axis which is parallel to the gravitational field. So in particular, you can see this from the fact that there is no phi in here. There is phi dot, but there is no dependence on phi. So this means that the phi is equal to 0. So we do have this symmetry. And the corresponding equations of the corresponding constant of motion, J, which is then the phi dot, that's going to be given by m r squared sine squared theta times phi dot. All right? And so this is essentially just the angular momentum. With respect to the z-axis. Because here r sine theta is the distance from the z-axis, and phi dot is the angular frequency with respect to that. Okay, so in this case, mu, if we go back and look what mu should be, so mu here should be the component of of the inertia tensor that corresponds to the coordinate that we're getting rid of. So in this case, phi. So this is m phi phi. And if we look at our original Lagrangian here, that's mr squared times sine squared theta. So that is going to be our m phi phi. Right? And lambda, we only have one lambda because we only have one additional coordinates. That would be equal to m theta phi, which is equal to m phi theta. And since we don't have any cross terms here, this is going to be equal to 0. So in this particular case, we can compute that our kappa, or kappa I, which j times lambda I divided by mu, well, since lambda was equal to 0, then kappa is also equal to 0. And so our Lagrangian is indeed in this case going to be that original Lagrangian that we guessed. So if we just compute the Hamiltonian, it's just going to be changing the sign of the potential term to get the effective Lagrangian. So the effective the effective Hamiltonian in this case is going to take the following form. We're going to get 1/2 mr squared theta dot squared plus 1/2 mr squared sine squared theta phi dot squared plus mgr cosine theta. Now this phi dot I can replace by solving for phi dot in the constant of motion up here in the angular momentum. And when I know replacement, what I end up with is 1/2 mr squared theta dot squared plus let's see if we get it correctly. Yeah, plus j squared divided by 2 mr squared sine squared theta. And then we have plus mgr cosine theta. And since our kappa was 0, this is going to be our kinetic term. And this is our effective potential. So this means that our effective Lagrangian in this case is just the same thing, but with a changed sign for the effective potential. So 1/2 mr squared theta dot squared minus the effective potential. So if we want to say something qualitative about this system, we can look at how the different contributions to the effective potential look like, just as we did before for the other type of scenario. So let me draw the following. Something like that. So if we have theta, and theta now goes from 0 to pi, and our original potential here looks something like this, modulo my drawing skills. That's the original potential. That's the gravitational term. To this, we have the addition from the fact that we have this angular momentum term in our potential in our effective potential. And that looks something like this. So we see that when sine theta goes to 0, which is at 0 and pi, this addition to the effective potential goes to infinity. So in particular, this means that if we draw the total effective potential, it's going to look something like this, right? Again, modulo my drawing skills. So this is the effective potential. And what you can see from this is that, well, the Hamiltonian observed. So what we have is the Hamiltonian consists of this kinetic term, and it consists of this effective potential term. Now, the kinetic term is greater than or equal to 0. So if we have a particular value for the Hamiltonian, say here, then the system cannot be in any position where the difference between the energy and the potential, the effective potential, is smaller than 0. So if we have this energy, if we have an energy around here, then we're going to be restricted to move within this region, because otherwise we would violate the conservation of energy. In particular, this means that since this angular momentum contribution goes to infinity, regardless of the energy we have, we will never be able to have this system reach theta equal to 0 or pi, as long as our angular momentum is non-zero. And this is one of the reasons why this term here, this term including the angular momentum, is often called the angular momentum barrier, because it's a barrier that prevents us from ever getting to these 2 points. Any questions on that?
Yeah, I mean, that's very unintuitive because it feels like it should be able to reach that point, or.
So the point is that it is able to reach that point if the angular momentum is 0. However, if the angular momentum is non-zero and you preserve angular momentum, so if you go, I mean,
all right,
if you go through 0, you don't have any moment arm for the angular momentum, right?
Mm.
So the angular momentum has to be 0 in that case.
Mm. Do you mean angular momentum around the z-axis?
Around the z-axis in this
Okay.
case. So this is what we have there.
Okay.
And we're going to see the same thing is going to be true if we move, for example, in a central potential, assuming that the central potential does not have any very unnice properties.
I didn't quite understand the horizontal line you drew as well, and the explanation.
This horizontal line.
Yeah, exactly. What?
So this represents the energy, so the value of the Hamiltonian.
Okay.
So if the value of the Hamiltonian is here, we know that since this kinetic term is positive, the Hamiltonian must be larger than the effective potential, wherever we are. Because this is the sum of those two, and this term is non-negative. So this Hamiltonian must be larger than or equal to this effective potential.
Okay.
So this means that we are restricted to move within this region.
Do you mean under it or just along
that
line?
No, I mean just within those values of theta.
Oh, okay.
So these points are actually called classical turning points. So as long as we're doing classical mechanics, what's going to happen is that at these points, theta dot is going to be equal to 0, because this is equal to this, and the only way that that can happen is if theta dot is equal to 0.
Mm.
So that means that at those points, theta dot is going to be 0, which means that this is going to be a point where theta dot changes sign. So what's going to happen is that if you start here and you move in that direction with this energy, you're going to arrive to there, and you're going to bounce back and forth like this.
Okay, that makes sense.
So those are called those 2 points where the energy is equal to the effective potential are called, or in general, if you have any one-dimensional system, it's called the classical turning points of that system. Then if you go to quantum mechanics, it's a different story, because then you can tunnel out and stuff like that. Any more questions regarding this before we go on? Okay, so this is actually a pretty good good introduction to what we're going to do next, because what we're going to do next is to discuss the period of oscillations. And what we're going to discuss is period of oscillations in one of those one-dimensional systems. So the assumption is going to be exactly what we have done so far now. So we're going to assume that we have some one-dimensional system with which is described by a coordinate q, and that we have some potential. It might be if we have a one-dimensional system from the beginning with potential v, or we have that this v is some effective potential, and then that effective potential looks something like that, right? And then we're going to be moving in this potential, and we're going to assume that we have some energy, which is, let's say, there. So this is the energy. And as we just said, if we start within, well, somewhere around here, then we're going to be restricted to moving between this point and this point, which are the classical turning points. But we can then ask ourselves, how long does it take for us to complete a full oscillation? So let's say to go from there, bounce there, and come back to the start. So that's what we're going to discuss now. So we have the classical turning points, which are here. And we're going to move then within those values of q. So we're just going to be restricted to moving here. Let's call them q1 and q2. So we're going to be moving within between those 2 values of q, just back and forth all the time. Now I assume that this potential does not depend on time, because if it does, then we're going to have to take that into account. But let's assume time independence of the potential. So that time independence, that tells us that energy is conserved. Right? And energy is just given by the value of the Hamiltonian. So that's going to be m½ q dot squared plus v of q. I mean, just assuming that we have a Lagrangian, which is m½ q dot squared minus v of q. This is going to be the Hamiltonian. And just to repeat the argument, since q dot squared is greater than or equal to 0, this means that that E is going to be greater than or equal to v of q, which is what means that we are going to be trapped to move between the classical turning points. And the classical turning points are then given by E equal to V of Q. So solving E equals V of Q will give you the classical turning points. Now, if I want to know how long it takes to go from one of the points, one of the turning points to the other, essentially what I want to do is to compute the integral of the t between those points. So, well, let's say I want to go back and forth. So let's call the time of one period, let's call that t. That means that I have to go back and forth from Q1 to Q2 and back again. And if I just compute half that time, it's going to be the time to go from Q1 to Q2. So that is a priori going to be given by the integral from Q1 to Q2, from Q equals to Q1 to Q2 of dt. But I can then change variables to use the coordinate Q instead. So this is the integral from Q1 to Q2 of dq dt inverse times dq. And this is just, let me just write this with the q dot instead. So this is dq q dot. But q dot we can solve from the Hamiltonian. We know the value of E, it's a constant of motion, and we know what V of Q is. So we can just solve for q dot from here and rewrite this integral as the square root of m, and still the integral from Q1 to Q2 dq divided by the square root of 2e minus 2 v of q. So this is going to be the period of oscillations, or half the period of oscillations, because I just went from Q1 to Q2. So I mean, if I write it for the actual time for one period, I multiply this by 2. So what I get is square root of 2m, the integral from Q1 to Q2 dq divided by E minus V of Q. Okay. And so let's note the following. As long as V prime of Q star, well, let Q star be one of these classical turning points, as long as that is non-zero, the integral converges. And if this instead is an equal sign, the integral diverges, which means essentially that if you have to climb a hill up to the maximum, so let's say that, for example, your energy would be instead up here, and you have to climb this hill up to the classical turning point, which happens to be a local maximum of the effective potential, then climbing that is going to take an infinite time. Of course, it's not really possible to exactly hit the correct energy to do that, but if you would have that possibility, then that would take infinite time. Any questions?
Yeah, just the intuition behind that. That it would take infinite time to reach.
Yeah, so the intuition you can maybe get if you do the reverse process. So if you take something and you put it as so let's take, for example, this this example that we had. No, well, let's take a bead moving on a ring that's standing still. Okay, so the top position is going to be an unstable equilibrium, right?
Right.
So if you start at the unstable equilibrium and you disturb it a small amount, it's going to very slowly in the beginning start diverging from that equilibrium.
Mm.
And that's kind of the opposite, well, the time reversal of the process we just discussed.
All right.
So I mean, it's the same thing, just in reverse.
Okay.
I mean, if you start at the unstable equilibrium, a priori you're not moving from there, but it's unstable. So for a very small disturbance from there, it's going to take very long to fall down. Yeah. Okay. So I mean, if the unstable equilibrium is the classical turning point, then essentially your time to reach that turning point, or to go away from that turning point equivalently, is going to go to infinity. Okay, so it's 10 minutes left, so we have time for an example. And so let me actually take that example because it's instructive. So the example is this bead on a ring, which is essentially just, I mean, it's just a pendulum if you remain at small angles and you don't have any risk of falling down. So you take a ring. Oops, that's not a ring. That's more like it. So let's take a mass moving on this ring, and let's call this angle S. Now your potential here, that's just V equals to mgz, which is the way we have defined S is minus mgr cosine of S. Okay, so if I let this go from some amplitude alpha, so if I take this mass here and I bring it up to here and I let it go, and this is alpha, so I let it go from rest at this point, and then I let it oscillate back and forth. Then I can ask myself what is going to be the period of those oscillations. So we have S max equals to alpha, and we have the energy, because at the beginning we have zero kinetic energy. So we can write that the energy is going to be equal to minus mgr cosine alpha, because when I release it from this amplitude, its energy is just going to be the potential energy, and the energy is conserved. So if I just take the expression for the period that we just wrote down, and I write it out, I'm going to end up with something like square root of 8r over g, and then integral from 0 to alpha. I mean, a priori you're going to have the integral from minus alpha to alpha, but since everything is symmetric here, it's sufficient to go from 0 to alpha and multiply by 2, which I have absorbed into this prefactor. And then ds divided by the square root of cosine S minus cosine alpha. So this would be the expression for this period. Now, for the case of small amplitudes, then we're going to have that cosine of s, well, it's approximately equal to 1 minus s squared divided by 2, and we're going to have higher order terms in s. So the same actually goes for cosine alpha, just changing s for alpha. And if I do that, that would mean that I have t equal to the same prefactor, 8r over g, the integral from 0 to alpha, the square root of 2 divided by then the difference, so alpha squared minus s squared ds. Just making a change of variables here, I'm going to get the following. So I get 4 square root of r over g, integral from 0 to 1, and I call my new variable tau. And I get the integral 1 minus tau squared. Now, this is an integral that you can actually perform using some trigonometric substitution. And what you end up with is 2 pi times square root of r divided by g. So this is, you might recognize as the small angle approximation, essentially the harmonic oscillator approximation of the period of the pendulum. So it works out in that limit, but if you go to a larger amplitude, then these harmonic potentials, which essentially is what we have here. Essentially, we are approximating the potential by a harmonic potential. In that case, if we have a larger amplitude, that harmonic approximation is no longer going to be good, and we're instead going to get a larger period. So it's no longer well approximated by a harmonic oscillator.